Okay, so this video is meant to fill in some gaps on that motional EMF example, which is here. Pretty much did most of it in the previous video, but actually finding the equations of motion is something that I need to fill in the gap on. That requires a little bit of calculus. So first, let me just get you back up to speed. What we have is this circuit where there's a loop, a conducting loop where the fourth side is movable. So this dimension stays fixed at L, but this dimension is going to increase, and that's where you're going to get that flux change. There's an external magnetic field, which I'm just calling B, so just to save myself some writing, when I say B, I mean B external. I don't need to do anything with any other magnetic field, so I'm just going to simplify that to B. And so that magnetic field sends some flux through here. Through Lenz's law, we can infer that the current is going to go counterclockwise, and then there's going to be force from that current. There's going to be a continued force on this bar that pulls backwards against the motion, and that is the kind of physical see with your own eyes manifestation of Lenz's law, is that you're trying to increase the flux by dragging this bar outward, and the force is acting to try to stop you. I guess, so that's I, by I mean I induced, of course. And then the L is this dimension, and then we'll say that this entire conducting loop has a resistance R. So what we found was the EMF is equal to BLV. That came from Faraday's law. And the EMF amount is tied to the speed of the bar. So when I have here the initial speed is going to determine the initial EMF, but as this thing slows down, and it will, of course, because the force of the bar is acting, the magnetic force acting against it, as this speed decreases, then the EMF will decrease. And going over here, just using Ohm's law, the induced current, again, I here means I induced, but there's no other currents of concern here, so I'll just shorten it. So the induced current is BLV over R. And so you can see, as the bar does slow down, then the current will get less. And remember that the whole force here, the magnetic force, is coming from that current, so the force will get less. And so what we're setting up here to do is to actually determine the equations of motion of how this thing comes to a stop. So here I have ILB, that's from, again, the previous thing. The sine of theta is 1 in this case. So what I'm going to do is I'm going to plug the EMF into here, like I did. There's my current, and that current is going to go in here. And then when I consolidate terms, here is my force. So you can see that the force itself is going to depend on the speed. So as this thing slows down, the force will get less. And what I want to work out here, my goal is to work out what is the actual velocity function with time. So here's what I'm going to do. I'm going to use this as my jumping off point, and I'm going to just plug it into good old F net equals ma. And so in this case, the net force on the bar is just the magnetic force, and so there's no other forces on this. So I'm just going to go ahead and put that in here. So that'll be BL squared V over R, just plugging in this, equals ma. And before I go too much further, now that I'm going to get serious about solving for the equations of motion, up here everything is in magnitudes, but here I do have a problem. If I look at A and B here, they have the same sign. So if V is plus, then A is plus. Now that's an issue because, of course, the force, the net force, and acceleration are the same way. The acceleration actually is actually opposite the velocity, otherwise you'd never slow down. So if they're in the same direction, you'd speed up. And of course that's not right. when I'm putting this together, I have to be a little bit mindful, not just using magnitudes, but I do need that they have opposite signs, otherwise you would never slow down. And so what I'm going to do here is I'm going to just throw in an extra minus sign here. So that's just basically a way to make sure that when I'm transitioning from over here, where everything's just sizes and magnitudes, over here, I do properly account for the fact that when you're slowing down, the acceleration and velocity are opposite to each other. So from here, this is what I'm solving for, and the acceleration, of course, going back to physics 1, acceleration is the rate at which the velocity changes. And what I'm going to do now is I'm just going to do what's called separation of variables. Like I guess even before that, I should point out that dv dt here is proportional to v. So what that tells me is that the rate of something is proportional to the amount itself. So when my speed of my bar is very high, I will also change it, so I will also decrease it very rapidly. That makes sense because when the bar is moving very fast, the flux change is very high, the EMF and current are very high, and that means that the force pulling against the motion is also very high. But in the limit that I slow down, when the bar is barely moving, well, the flux change is almost nothing, so the EMF and current are very small, and the force acting against it are very small. And I just point this out to remind you that anytime you see when the rate of something is tied to the amount itself, you are expecting an exponential function, so that is what we're going to get. So let's go ahead and work out the details. If you actually go ahead and work out, not just that they're proportional, the proportionality constant, just basically just have to bring the mass down here. So that'll be BL squared over R times M, and then we have a V. So you can indeed see that they're proportional, and the proportionality constant is this right here. So at this point, we are ready to do the separation of variables technique. We'll put all the V stuff on one side, all the non-V stuff on the other side, and this constant, I'm going to group it. I'm going to call this 1 over tau. So over here, not including the minus sign. So the minus sign does not go into tau. I'll keep it out here in the front. And so now, we have put all the V stuff over here, and I guess I should write down over here, tau looks like this. And now we're ready to integrate. So let's go ahead and do that. We're going to integrate both sides. And just so I don't have to deal with a plus c, I'm just going to put my integration bounds into the, put my initial conditions into the bounds, right? If you want to avoid indefinite integrals, which have the plus c, you just go ahead and put them into the integration bounds. So I'm going to start at t equals 0, where my velocity is v initial, and then I'm going to go out to some random time t, where I have some random velocity v. So I integrate here, dv over v is natural log, and then of course I evaluate over the bounds, and over here, integral of dt, well this is just a constant, so integral of dt is t, evaluated from 0 to t is still t. So now we have our integration done. We just go ahead and solve for the velocity, and this is what you get. We get a very familiar looking thing. This of course is the velocity as a function of time. We get a very familiar exponential. We've looked at a lot of these in RC circuits. So let's go ahead and draw that. There we have it. The velocity will decrease with time, and it starts off at initial velocity and then decreases towards 0. It takes forever to go to 0 exactly. And that's of course because the slower you go, right, the slower this bar moves, the less the braking gets, right? If v is almost 0, EMF and current are almost zero, and the force is almost zero. So these, of course, we use tau instead. Tau is the time it takes before it's lost. It's now 37% of its initial velocity, having lost 63%. We can look at what goes into tau, make sure that it makes sense. So I guess I have it right here, I don't need to recopy it. So this tells us that if B, the magnetic field, or the length of the bar are larger, that is going to reduce tau. In other words, we're going to reach this benchmark quicker, right? So we are slowing down more quickly. So we have quicker braking. We're going to get to 37% of our initial velocity quicker. Now, why is the magnetic field being stronger or the length being longer? Why do those make it so that we reach this benchmark quicker? Both of these, both B being larger and L being larger, are going to increase the magnetic force at any given speed. So FB, the braking force, is larger at any given moment. Okay, so no wonder we brake more quickly. Then we have the two factors on the numerator. If we make the mass of the bar larger, or we make the resistance here larger, I guess I should label what I mean by M here, of course, is the mass of the bar, if that wasn't obvious. So if we make the mass of the bar larger, or we make the resistance larger, those will actually both drive tau to be larger, so we will get slower braking. We will not reach this benchmark quite as fast, so a larger tau, of course, would look something like this. So larger tau, it would take longer before we hit this 37% of our initial velocity. Let's think about why this makes conceptual sense. Of course, M being larger just means that the bar has more inertia. It's harder to brake it. And then the resistance being larger, well, of course, a large resistor is going to hold back the current. So for any given EMF, the resistance being larger is going to make the current smaller. And if the current's smaller, then the force will be smaller. So this will mean that the current is less, which makes the magnetic force less. And so no wonder we get slower braking. So that's a quick tour of how you might solve the equations of motion here and why it makes sense. I do want to point out that the braking here is exponential, so you would never truly stop. For instance, when they use magnetic braking, that's sort of like this. For instance, they use this a lot on like high-speed rail or like specialized roller coasters. They use magnetic braking because it's very powerful. However, at some point, when you slow down enough, they do switch to conventional braking, which is just based on kinetic friction because, of course, you don't want to wait forever to slow down. So this is kind of used in many systems as a way to initiate braking without having a huge amount of kinetic friction that wears out the surfaces over time. If you have like a high-speed train that's stopping from 200 miles an hour, you'd have to replace the brake pads pretty often. So oftentimes you use something like this, which of course is pretty much touchless braking, and then you switch to more conventional braking once you slow down enough. Now, as far as the practicalities of how you might implement this on the homework, essentially F net equals ma is your friend. The force, net force, will come usually, at least in part, from a magnetic force. Be on the lookout if there are other forces. You of course need to include all of them in F net. And then F net equals ma, A equals dv dt, and dv dt is on this side. Usually there's some sort of velocity dependent force for the magnetic force. And at that point you're going to do a separation of variables and get some sort of function like this. Do be careful, of course, when you're putting it all together into F net equals ma to make sure that the relative signs of the acceleration and velocity make sense. If you're slowing down, then velocity and acceleration can't have the same sign. So you'll need to potentially consider throwing in an extra minus sign, because if we hadn't done that, of course, the velocity would be blowing up exponentially, not decaying exponentially.